On January 18th, 2026, airline pilots flying over the Pacific received an alert they'd never seen before. Not turbulence, not a mechanical warning. NOAA had just classified a solar radiation storm as S4, severe, one step below the maximum. The last time that happened, October 2003, over 20 years ago. But the radiation storm was just the beginning. What followed would light up skies from Canada to Alabama, force astronauts to take shelter, and remind us that the sun doesn't care about our schedules. Here's what most people missed about that day. At 1:09 p.m. Eastern Time, observatories around the world detected a massive coronal mass ejection erupting from the sun's surface. The flare that triggered it was classified as X1.9, the most intense category solar flares can reach. Within the X-class scale, it ranked as one of the strongest in recent memory. But the October 2003 flare, that one was so powerful it literally broke the instruments. The detectors maxed out at X17 before they failed. Scientists later estimated the true strength at X45. So why should you care about X1.9? Because the radiation arrived before the plasma did. Solar energetic particles, mostly protons, travel at nearly the speed of light. They reached Earth within minutes, not hours. And when they slammed into our atmosphere, the radiation levels spiked to S4. That's the second highest level on NOAA's scale. At S4, high-frequency radio communications black out. Satellite electronics can be damaged, and anyone flying at high altitude receives elevated radiation exposure. Here's the part that should concern you. While the rest of us went about our day, astronauts aboard the International Space Station received urgent instructions: get to the shelter areas. Now, the ISS has two modules designed to provide extra radiation shielding, the American Destiny module and Russia's Zvezda. During severe solar events, crews are trained to abandon their normal work and take cover. On January 18th, they did exactly that. Because in space, there's no atmosphere to protect you, no magnetic field to deflect the particles, just a thin metal hull between you and the full fury of the sun. But the astronauts weren't the only ones affected. As the CME followed the radiation storm slamming into Earth's magnetosphere hours later, geomagnetic conditions escalated rapidly. NOAA upgraded the forecast from G3 to G4, severe. The KP index, which measures geomagnetic disturbance, climbed to 8. At those levels, power grids experience voltage irregularities. Satellite orientation systems can fail, and the aurora, normally confined to polar regions, expands dramatically southward. That night, people in Alabama saw the northern lights. Florida, Texas, places that might witness such displays once in a generation, suddenly had front row seats to one of nature's most spectacular shows. Social media exploded with photographs, green curtains rippling across suburban skies, purple bands dancing over golf courses. For a few hours, the terror of the radiation storm gave way to wonder. But let's be clear about what actually happened. The sun, our nearest star, had just reminded humanity of something we tend to forget. We live inside its atmosphere. The solar wind, the constant stream of charged particles flowing outward from the sun, extends far beyond the orbit of Pluto. Earth orbits within this stream, and occasionally, the sun sneezes. A coronal mass ejection is essentially a solar sneeze. Billions of tons of magnetized plasma, expelled at millions of miles per hour. Most of the time, these eruptions miss Earth entirely. Space is vast, and we are small, but when one hits us directly, the consequences depend entirely on how prepared we are. In 2003, the Halloween storms caused widespread satellite failures and a power blackout in Sweden. In 1989, a G5 storm knocked out power across Quebec in 92 seconds. And in 1859, the Carrington event set telegraph offices on fire. The January 2026 storm didn't reach those levels, but it came closer than anything in 2 decades. And it happened during what's supposed to be the declining phase of solar cycle 25. The sun, it seems, didn't read the forecast. So what does this mean for the future? Solar physicists are revising their models. The current cycle has consistently exceeded predictions. More X-class flares have erupted than expected, more severe storms have reached Earth. And while no single event has caused catastrophic damage yet, the pattern is clear. We're in an active period, and active periods produce surprises. The January storm was a warning shot. The infrastructure held. The astronauts are fine. The power stayed on. But somewhere in that success is a dangerous assumption that we'll always be this lucky. The next time the sun fires an X-class flare directly at Earth, will we be ready, or will we be standing in the dark, looking up at an aurora we never expected to see, wondering why nobody told us this could happen? If you saw the aurora in January, where were you? And did you know what was actually causing it?